Namaskaram. In last class, we have discussed about directional derivative. In this session, we will discuss and we define the gradient and its properties with the help of directional derivative. These are the solutions of last homework. One crucial application of gradient is in machine learning. Every machine learning algorithm contains two phases. One is forward pass and other is backward pass. And this backward pass is called backpropagation. In forward pass, machine evaluates an error with the help of given input data. In backward pass, we have to minimize our error function as far as possible by adjusting weights and biases. These weights and biases are the technical term in neural network, and actually they are like our variables x, y, and z, like that. Okay, in the case of machine learning algorithms, maybe number of variables means these weights and biases maybe millions and millions, or 3 millions, like that, or 10 million, maybe like that. Okay, to minimize this error function, all the machine learning algorithms use gradient descent and its variants. And the backbone of gradient descent is our gradient. So this is the one important application of gradient in machine learning. We have seen that this representation of directional derivative, if you use a unit vector and x0 y0 is a given point, then the directional derivative of the function f at this point in this direction is given by this formula. Okay, we can rewrite this as in terms of vector product. That means our dot product in vector calculus. So this is the another representation of the same equation, fx x0 y0 I plus fy x0 y0 j dot u1 I plus u2 j. Now they are two vectors and you consider the dot product of two vectors. And we know how to expand this dot product, fx into u1 plus fy into u2. That is same as this formula. Okay, so this is a vector representation of the same directional derivative formula. Similarly, we can find the dot product of these two vectors gives the same formula for three-dimensional keys. Okay. So in both cases, the directional derivative is obtained by dotting the new vector. The new vector. What is new vector? This is our new vector. Okay. In the case of 2D, this is our new vector. In the case of 3D, this is our new vector. The new vector formed from the first order partial derivatives of f with a unit direction vector u. Here, this is our vector u. In this case, this is 2D unit vector. This is a 3D unit vector. Okay, now we have a new vector in terms of partial derivative. And we define this new vector as our gradient of a function f at this point. Okay, so if it is general gradient, then we simply write fx xy fi plus fy xy. That's all. Okay, this is actually gradient at a particular point. Okay, and this new vector is called gradient. In the two-dimensional case, this is the gradient of f, and this is the gradient of f in three-dimensional case at a particular point. Okay, now we are ready to define the gradient formally. So this is the formal definition of gradient in arbitrary point. The gradient of a function fxy, this is a two-variable case, is defined by fxy I plus fy of xy j. What is fx? Fx stands for the partial derivative of f with respect to x, and fy stands for the partial derivative with respect to y, and denoted by del f. Okay, and we call this notation as either del actually or nabla. Okay, normally we call this symbol as del. So this is called del f. Okay, del f. So what is del f? Del f is called the gradient of the function, and it is defined like this. In the case of three variable case, del f is defined like this. Okay. So del f is always a vector using partial derivatives. So with the help of this new representation or new definition, we can write our directional derivative as like this. Directional derivative of f at this particular point is equal to del f at that point dot u. Okay, u is the unit vector. In the case of 3D, this is equal to, again, left side is again del f, but only difference is here it involves three variables. Okay, dot u. Now it is clear that this u is a three-dimensional unit vector. Okay. Del f is not only a vector, it has so many properties. The magnitude and direction of gradient del f, gradient means del f. This f may be two-dimensional or three-dimensional, whatever be, gives in general it has any dimension. Okay, we will discuss only 2 and 3 dimension. In general, the function may be in any dimension. In the case of machine learning functions, the error function has millions of variables are there. They are called weights and biases. Okay, anyway, the magnitude and direction of gradient del f gives important information about the function f and the surface. Surface means the function corresponding to this function, the surface corresponding to this function. For example, suppose our function is a two variable function. Then you can think about a surface like z is equal to fxy. Okay. In the case of three variable, it is like w is equal to fx, y, z. Okay, we can't imagine the surface, but such surfaces are called hypersurfaces in higher dimension. Okay. Anyway, gradient has some important properties. Okay, we know that directional derivative, suppose del f is not equal to 0, then we know that the directional derivative in a particular direction u is equal to del f dot u. Okay, we have seen that, this formula, del f dot u. And what about a dot b? Now the both are vectors. Then we know how to dot two vectors. That is nothing. It is modulus of, if a dot b is equal to mod a mod b cos theta. So this become modulus of del f and modulus of u into cos theta. Okay. And what is theta? Theta is the angle between del f and u. Okay. So this is the representation of directional derivative in terms of cos theta and something. So my question, what is the maximum value of a directional derivative at a particular given point xy? Okay, we fix a point xy. Then my question, what is the maximum directional derivative and in which direction? Okay, to find the maximum, it is clear that this is mod del f at a particular point. U is fixed. U is always a unit vector. So its modulus value is always 1. Isn't it? So again, we can write this as, this is our normal product. This is not a dot product. This is a normal multiplication. This is mod del f. Now we consider the two variable case, del f of xy into cos theta. And what is the maximum value of this? If we fix a point xy at somewhere, then this quantity is already fixed. Okay, and now the value of this product depends only on theta. Okay, then what is the maximum value of cos theta? That is 1. So this value, the maximum value of this directional derivative at a particular point is attained when theta equal to 0. Okay, so when theta equal to 0, it attains its maximum. You got it. And what is the maximum value? The corresponding maximum value is modulus of del f. And maximum occurred when theta equal to 0, and the maximum directional derivative is modulus of del f at that point. So which direction gives the maximum rate of change or maximum directional derivative? Yeah, that is corresponding to theta equal to 0. Theta equal to 0 means angle between u and del f is 0. That means u and del f in the same direction. Okay. So maximum rate of change is given when u is in the direction of del f. Okay, if u is in the direction of del f, the function has maximum rate of change. So in this case, u also in the same direction of del f. Okay. Then there is another question. Similarly, we have another question, which is the minimum value of the directional derivative at this point and in which direction. Okay. Okay, again from this same formula, it is clear that this is mod del f into cos theta. This is fixed at a particular point. So the value depends only on cos theta, that is theta. So what is the minimum value of theta? What is the minimum value of cos theta? We know that the minimum value of cos theta is -1 occurred when theta equal to pi. When theta equal to pi, cos pi is -1. Okay, so when theta equal to pi, this is the minimum. The minimum of the directional derivative at a particular point when theta equal to pi. And what is the minimum value? The minimum value of del u is equal to, whenever theta equal to pi, this become -1, this become minus of mod del f. Okay, so this is the maximum value of directional derivative at a particular point. This is the minimum value of the directional derivative at a particular point. And again, there is a question, which is the direction such that this directional derivative is minimum. Theta equal to pi means what? Theta is the angle between this gradient vector and unit vector. So angle is pi. Angle is pi means the direction of unit vector is opposite of this vector. So this is the direction of minus del f. Okay. So u is in this direction. So if u is opposite of del f, then that direction gives the minimum rate of change. That means the function decreases more rapidly in this direction. That is, function decreases more rapidly in this direction if we move in this direction. Okay, that is the core idea of gradient descent. Okay, this is the graphical representation of the concept. Suppose we have a function z is equal to fxy, and we consider the particular point, and we have to find del f and minus del f. What is del f? In this direction, function increases most rapidly. Okay, that's idea. Okay, and in the opposite of this direction, that is minus del f direction. In this direction, function decreasing most rapidly. Okay, so in the machine learning algorithm, in each iteration, always we move in this direction, minus del f direction, to decrease our error function. Okay. Okay, next we are going to summarize all these properties of gradient. If f is a function of either 2 or 3 variables, and let p denote the point p, either p of x 0 y 0 or p of x 0 y 0 z 0 respectively. In general, this function may be in any number of variables. Okay, in general, it is n variable case. Then we can write du of, that means directional derivative of function at u, can be written in the form del f dot u. Okay, whatever be the dimension of the function, you can always write this is a del f dot u. Then another property is, suppose del f is 0. Suppose del f equal to 0 at a particular point. Then what happened? Whatever be the direction, directional derivative is always equal to 0 dot u. We know that 0 dot u equal to 0. Okay, so that is another property. So if del f equal to 0 at a particular point, then in whatever be the direction, its directional derivative is always 0. Okay, because due to this formula. And next observation is the maximum rate of change of the function f is in the direction of the gradient, and the maximum rate of change is mod del f. Okay. And we have one more observation. The minimum rate of change of f is in the direction that is opposite of the gradient, that is minus del f direction. Okay, and the minimum rate of change is minus of modulus of del f. These are the observations of the gradient. These are the properties of gradient. And this fourth one, this is the backbone of all the machine learning algorithms. Okay, this is the crucial concept. Consider a problem that fxy is equal to x square e raised to y. Find the maximum value of the directional derivative at minus to 0, and find the unit vector in the direction in which the maximum value occur. So from previous discussion, it is clear that the maximum value of the directional derivative is nothing. It is modulus of del f at this point minus to 0, and which is the max what about the direction corresponding to this maximum rate of change? This direction is del f at this point. Okay, but only thing is we have to find the unit vector. We have to find the unit vector. This is in general del f need not be unit. So if it is not unit, then we can easily find the unit vector by dividing its modulus. Okay, so this is the concept behind this problem. So okay, so we know that del f is nothing. It is equal to fxi plus fyj. X and fi are the partial derivatives. So you simply differentiate this with respect to x. If you differentiate with respect to x, what happened? This is 2x e raised to y. So that's why this is 2x e raised to y I plus, and we differentiate with respect to y. This is same as x square e raised to y. So x square e raised to yj. And we have to compute del f at a particular point. So del f at a particular point minus 2 0 is you simply replacing x by minus 2 and y by 0. Then we get minus 4i plus 4j. So this is the direction, but it is clear that this is not a unit vector. If you take the modulus of this one, is not equal to 1. Okay, anyway, we have to find the maximum rate of change. What is maximum rate of change? This is the maximum rate of change. So modulus of del f at minus 2 0 gives the maximum rate of change. So what about the modulus? You take the positive square root of minus 4 square plus 4 square. That is equal to, okay, this is equal to square root of 32, 16 plus 16, 32. And square root of 32 is 4 root 2. So this is the maximum rate of change. Okay, then which direction? And we have to find the unit vector in that direction. This is the vector, but this is not unit because its norm is 4 root 2. So if it is unit, then its norm should be 1. Okay, since it is not 1, we have to find the unit vector. How to find unit vector? By dividing its modulus. So here modulus is 4 root 2. So 1 by 4 root 2 into del f. Del f is this one at that point. So by simplification, we get divert. So this is the unit vector and this is the maximum rate of change. That's it. This is our del f 0. Okay. Okay, consider next problem. A heat-seeking particle is located at the point 23 on a flat metal plate whose temperature at point xy is given by this formula. Txy is equal to 10 minus 8x square minus 2y square. Find an equation of trajectory of the particle if it moves continuously in the direction of maximum temperature increase. Okay, so that's the idea. So this is our 2, 3 somewhere here, and this is a metal plate, and it is clear that its maximum temperature is actually at 0 0, because this is 10 minus 8x square minus 2y square. We can rewrite this as 10 minus 8x square plus 2y square. So this is always non-negative. So its maximum is when it is 0. So that is at origin. Okay, but the particle is moving in this principle. What is the principle? The particle is always moving continuously in the direction of maximum temperature increase. So what is the idea? So we have a temperature distribution along this metal plate. So the core idea is, first of all, we compute the gradient at this point. Okay, then we identify the del f direction. Del f direction gives the maximum rate of change of the temperature. So first of all, this particle move in this direction. Okay, again it calculates continuously. It calculates the gradient at this point. Suppose gradient at this point is maybe this direction. Then it moves in this direction. Again it calculates the gradient continuously at this point. So it move slowly converging to this point. This is the principle of heat-seeking missiles. Okay, they use some infrared sensors to compute this temperature gradient. Maybe some fighter in front of another fighter flight. So they calculate this temperature gradient using infrared sensors and heat-seeking particle moving and hit the target using this principle. Okay. Let r of t is equal to x of t I plus y of t. Let r of t is equal to x of t I plus y of t j be the trajectory of the particle. Okay, in this graph, this is the trajectory of the particle. So we have to find equation of this path. Okay, the maximum temperature change path, r of t, where t is the time parameter. It is given that initially this particle at the point 2 3. That means what? That means r of 0 is given. R of 0 is nothing, 2i plus 3j. What is R of 0 from this expression? That is x of 0 I plus y of 0 j. So it is clear that x of 0 equal to 2 and y of 0 equal to 3. So this is an initial condition that is given. Initially the point at the particle at 2, 3. Okay, how to find the velocity of this particle? Suppose we are computing the velocity at each point. Okay, and this is the trajectory of the particle. We assume that this is our trajectory. Okay, so how to find the velocity? So we know that velocity is equal to dr by dt. Okay, so in this case it is x dash of t I plus y dash of t j. And what is the direction of velocity? What is the direction of velocity? The direction of velocity is the direction of gradient. Why? Because the particle always moves in the direction of maximum temperature increase. That is the direction of gradient. Okay, so the direction of velocity always in the direction of a gradient. Only its magnitude may differ. So what happened? So velocity can be written as some scalar times, because magnitude may differ. So scalar times uh, gradient of t. So velocity can be written as k into delta t, gradient of the temperature function. You got it? So by simplifying this, we get like this. Okay, what is a gradient? What is delta t? And we can compute the delta t. Delta t is equal to, first of all, you differentiate with respect to x. So this become minus 16x I. Again you differentiate with respect to y, so this become again a minus 4y j. So this is the gradient of this temperature function. Okay, it's clear that the velocity is always the multiple of gradient, because velocity and gradient in the same direction, because we have to maximum rate of change of the temperature. Okay, so this become like this: dx by dt I plus dy by dt j is equal to k times our gradient is this one, minus 16xi minus 4yj. By comparing the terms of I and j, we get two differential equations. Okay, these are the two differential equations. Dx by dt is equal to minus 16kx, and comparing the coefficient of j, we get dy by dt is equal to minus 4 ky. Next, we can find dy by dx by dividing these two equations. Suppose this is our first equation, this is our second equation. By next we consider 2 by 1. By dividing 2 by 1, we get dy by dx, isn't it? So that is possible. So what is dy by dx? So by dividing 2 by 1, we get dy by dx is equal to minus 4ky by minus 16kx. After simplification, we get y by 4x. Now we have a differential equation. Dy by dx is equal to y by 4x. It is clear that it is separable. You can separate this differential equation. Okay, our ultimate is to find this trajectory. That means we have to find x and y. Okay, now we have a differential equation satisfying x and y. And also we have one initial condition. The initial condition is this one. Whenever x equal to 2, y equal to 3. That's our initial condition. Okay, so we have one initial condition, y of 2. That means when x equal to, what is the y value? 3. So ultimately we have to solve this initial value problem. So now our problem is reduced to solve this initial value problem. It's very easy to solve because this is a variable separable form. Okay, I just rewrite this equation. So our aim is to solve this different initial value problem to get this trajectory. We can separate this like this: dy by y is equal to dx by 4x. Then by integrating on both sides, we get uh, log y is equal to 1 by 4 log x plus a constant of integration. We can take it as log c. And this implies what? This is log y is equal to, this is log x raised to 1 by 4 plus log c. Again, you can take on left side. So this becomes log a minus log b. That is log a by b. So this becomes log y by x raised to 1 by 4 equal to log c. You can cancel log on both sides. we get y by x raised to 1 by 4 is equal to c. So this implies our trajectory y satisfies c into x raised to 1 by 4. Then how to find c? C is a constant. To find c, we can use this condition. Whenever x equal to y is equal to 3, that is given. So you simply substitute x equal to 3. So what happened? When x equal to 3 and when x equal to 2, y is equal to 3. So y of 2 equal to 3 implies 3 equal to c times 2 raised to 1 by 4. This implies c equal to 3 by 2 raised to 1 by 4. So what is our trajectory? So our trajectory, final trajectory, y is equal to, what is c? C is 3 by 2 raised to 1 by 4 into x raised to 1 by 4. So this is the trajectory of the particle. So particle moves in this trajectory. And finally, it reaches the maximum temperature point by using our gradient technique. Okay. Yes, y is equal to 3 by square root of 4, square root of, 3 by 4th root of 2 into x raised to 1 by 4. And this is the graphical, this is the graphical representation of this problem. And in this first picture, we plot our temperature function. This is actually our temperature function T. Because x and y moving in 2 dimension, and we have one more thing, that is our temperature function. We plot the temperature function on the z axis. Okay, then we get a surface like this. Okay, and we have to find the isotemperature curves. Isotemperature curve means those curves with the same temperature. So it is clear that, suppose we consider this green ellipse. What is the meaning? On this green ellipse, it has same temperature. You can find almost what is the value of temperature on this graph. Maybe it is minus 40 or whatever be, and its maximum temperature is 10. Okay, that's why this is this point is 10. Okay, maximum is at this point. This is our origin. Okay, and presently our point is at 2 3. 2 3 means these are x-axis 2 and 3. 2 3 is somewhere here. Okay, actually the path is like this one. So it is going this direction, and finally it's using our gradient method. Okay. Okay, next I will give a brief idea of gradient descent. Suppose this is our error function. I just plot our error function on this in the z axis, and we have only two unknowns. Weights and biases are only two. Suppose it is two. Okay, in general, the weights and biases are millions. Okay, so suppose this is our current position of our weights and biases. We have to find this optimum point by reducing our error function. Okay, so the natural question is how to move more rapidly to this point, from this point. Okay, so which direction gives the more rapid decrease? The direction is nothing. You move in the direction of minus del f at this point, that means in this direction, that gives the most rapid decrease. Okay, so in each backpropagation phase, machine computes the gradient. Okay. In each iteration, machine suppose this is the present state, then machine computes the gradient and move in the direction of negative del f. Okay, until it reach this point. Okay, so maybe if you take the gradient and maybe direction like this, so it move like this. Again, it compute the gradient and it take the minus, so maybe like this. So ultimately, it reach this minimum point. This is the core idea of gradient descent. Okay, so these are the homeworks for this session. Thank you. Okay, please comment your suggestions in comment box. Thank you.